Hello, sir. Good evening.
Good evening, Narendra.
Good evening, sir.
How are you?
Yes, fine, sir.
Okay, so it's 6:04. We'll wait for some time. You are able to see my screen, right?
Yes, sir.
Okay, okay. Let's see. Yes, Mm, okay, so it's 6:05. I think we should start. Maybe other people will join or not. We don't know. So anyway, like we used to do normally, what I will do is revision in 15-20 minutes. Then we'll solve some problems. First was Clausius. One second. Spelling. I think the spelling is correct only. Clausius inequality. It is basically for all cycles or cyclic process, cyclic integral of inexact differential of del q by t is less than or equal to 0. The equality holds when the process is reversible completely, or the cycle is completely reversible, internal as well as external. So since we are here, we can take one simple problem where this is used. The question is like this. This is a previous year gate question. It's an old question, but it's still interesting. There is a system in which there are three temperature reservoirs at T1, T2, T3, and one heat engine is operating by exchanging heat with these three reservoirs, and it is giving you maybe like there is some temperature sink TL, and this is a reversible heat engine. It is given in the question, and from this heat engine you are getting some work output. So uh, it is given that T1 is 1000 Kelvin, T2 is 500 Kelvin, T3 is 300 Kelvin. Nothing is mentioned about the sink temperature, and it is asked that uh, you need to find efficiency of this reversible heat engine. This is a 2 mark question in a gate exam, mechanical exam. So now to solve this question, see, the formula of efficiency is total work done or net work done upon heat input. But here, uh, one more data is given. Q1 is equal to 100 kilojoule. Q2 is equal to 50 kilojoule. Q3 is unknown. So work done is unknown, Q3 is unknown. So you can't directly apply that net work done by total heat supplied formula. So here you can use Clausius inequality since it is mentioned that it's a reversible cycle. So you can write from Clausius inequality cyclic integral of del q by t equal to 0. In class, professor write it like this: del q. I just write d and some this cross mark to indicate it's an inexact differential equation, differential variable. You can do both ways; both are fine, but it's just a notation. Don't get confused or anything. Okay. So now, how do you use it? You apply this inequality to the heat engine. And as per our convention, if we take this heat engine as our system, whatever heat is coming to the... Oh, okay. I am sorry, I made a mistake. This T3 itself is a sink. I forgot to see the arrow actually. So, 1 second, I'll just modify the image slightly. So this is going to the sink and you are getting some work output which is unknown. So you have two source and one sink. It's not a simple problem with one heat source and one heat sink. So now here you can apply Clausius inequality considering the heat engine as your system, reversible heat engine. If you do that, Q1 by T1, it will be positive since it's coming to the engine. Again Q2 by T2, and since heat is leaving, Q3 amount of heat is leaving the engine, it will be negative. And here you need not to worry about the integral because it's a constant temperature source. So even if you do the integral, 1 by T will come out. So it will be just integrating del Q. So it is Q. So therefore you can just write this way. So now if you see, you know T1, T2, T3, you know Q1, Q2, Q3 is unknown, right? So one equation, one unknown. You can solve. So it will become 1000 by, I think T1 is 1000 Kelvin, 100 by 1000. Q2 is 50 by 500 minus Q3 by T3 is 300. This has to be 0. So this both fraction are 110, 110. So it is 210, 15. So basically Q3 will be 300 by 5. It is 60 kilojoule. Now you need for calculating efficiency, you need work output also. So here you'll apply first law for by first law of thermodynamics applied to reversible heat engine. What is the first law for a cyclic process or the device operating in a cycle? Total heat interaction is equal to the total work interaction, right? This is the first law. So here total heat interaction is plus Q1 plus Q2 minus Q3, and total work interaction is W. It will be positive because it is work done by the system. So now you can find total work done as Q1 is 100 plus Q2 is 50, Q3 is 60. So if you do this, it should be 90 kilojoule, right? 150 minus 60, 90. Now you can calculate the efficiency of this reversible heat engine, which will be W by the heat supplied is Q1 plus Q2. Q3 is heat rejected. So it is essentially 90 by 100 plus 50. So it is 9 by 15. So it is 3 by 5. It is 0.6. So it's 60% basically. Let me just check the answer if I'm not doing any mistake. Yes, the the efficiency is 60%. So this is your answer. So here, this is a nice example where you use first law also to calculate work done. You use Clausius inequality to calculate the heat rejected to the sink, and then you use efficiency formula. Basically, first law, second law combined. Clausius inequality is essentially a part of second law only, you can say, in a sense. So therefore, this is a good example just to get warmed up. Now, after that, there are two TDS equations. I mean, this is a common terminology. We call it TDS equations because they involve TDS. So basically, you define a property which is like this. You take one reversible path, one irreversible path, and a cycle, and then you write this inequality, which is ds del q by t equal to ds. This is like del q is not a property; it's a you can call it as a boundary phenomena, but this ds, it's a property. It's a very confusing question, very confusing statement. Many a times interviewers will catch you here if you don't understand this properly. What we have done is this del q is a inexact differential, so we multiply by the integration factor or integrating factor if, we call it, which is 1 by t, temperature inverse, and then we convert this inexact differential in an exact differential, and that becomes a property of your system. So therefore you can write del q as TDS. So then the first law is del q equal to du plus pdv. Mind you, this is a common mistake that people do. Sometimes in hurry they will write this as small ds, like d small s, and here they'll write capital U capital V. So that's a wrong equation. It will not satisfy the unit balance. So these are multiplied by mass. Internal energy, it is in joules, not joule per kg. Volume is like this. PdV is also in joule, not joule per kg. So this TDS should also be in joule, not in joule per kg. So these are extensive properties. You can say U, V, P, T, S. So this is one TDS equation. Then there is another TDS equation, which is also like, you can do some manipulation. You can just write, how should I write? Okay, so I can write differential of PV as PdV plus VdP, right? So I therefore PdV is dPV minus VdP. This is not a small v, this is a capital V, VdP, and put this here in equation 1. You will get TDS equal to du plus dPV minus VdP, and this is, by differentiation you can write it this way, and it becomes dH minus VdP. At this point, these equations may look trivial to you, but like if you study thermodynamic relationships, these will come in handy. There you use it multiple times. So based on that, there was one derivation by professor where you derive for reversible adiabatic process. adiabatic process, you get PV power gamma equal to C, where gamma is Cp by Cv. They have some name for it, some index or something. I forgot what is the name of gamma. Normally we use it as gamma only. So this is there. And reversible adiabatic process, it is also called as isentropic process. This is also a very favorite 1 mark question in GATE or engineering services or civils. They'll try to confuse you. What is isentropic process? One option will be reversible adiabatic, one will be isothermal adiabatic, one will be something. But you should remember, if it is reversible as well as adiabatic, then only it's isentropic. So because when it is reversible, there is no entropy generation. Essentially, what you write, ds of your system will be this, not cyclic here, it can be like this only for a process. It will be del q by del t plus some ds generation. So when your process is reversible, this goes to 0. When it is adiabatic, this goes to 0. So the whole term is 0. So your system ds is 0. Even you can call surrounding also 0 because there is no dq, and therefore it's a reversible adiabatic process and it's also isentropic process. So this is one. One more thing was, it is also important, professor told you about Carnot cycle, right? So if you plot it on TS plot, it looks like this. It will be a clockwise cycle since it's a work producing cycle. These two are constant temperature processes and these are constant entropy processes. So one more very common question is asked mainly during interviews is plot Carnot cycle on PV plot. So how will it look like on PV plot? So that is a very common question. So if you do this way, so now you should know what is the slope of isothermal line, or how do you represent isothermal line, which are these two constant temperature lines, and how do you represent constant entropy lines. So you can look into this also. I think I have it somewhere. 1 second. Carnot cycle. So basically what is happening is, let's number these processes just to just to be 1 second. Yeah, we can rename this point as 1 2 3 4. So between 1 to 2, what you are doing is essentially you are doing what is it called, like you are doing reversible adiabatic compression, which is isentropic compression. So your temperature is increasing but your entropy is constant. So generally when you show it on PV plot, it's a compression process, so it will be something like this. If I am not wrong, it will be something like this, and it will go this way because during compression your this thing increases. What do you call? Pressure increases, volume decreases, pressure and temperature also increases. So this line will somewhat look like this, and this will be your 1 2. Then you have isothermal process, so it will go like this. It will not be a linear line, it will be something like this only. It will be 3. Again, it's a isentropic expansion, 3 to 4. So it will look like this, and you'll arrive at 0.4. And then you'll have compression back from 4 to 1. Actually, these lines will be very close to each other. I'm not able to show it properly here. So 1 to 2 will be constant entropy. These are constant temperature. This is also constant entropy. So this question they ask usually. Now, one thing is there. Actually, I forgot. See, you can ask me, that how did you draw this part, CPCV, right? So, I think it comes from TDS equation only somehow. But anyway, my point was, if you are aware of TS plot for Carnot cycle, you should be aware of PV plot for Carnot cycle also, Carnot engine, whatever it is. You can see this area under the curve will give you the net heat supplied to the system, and this is work done. So essentially the takeaway is that work done or work output, net work output from the Carnot cycle is very low, even though its efficiency is maximum, because we know eta is 1 minus TL by TH. Work done is not maximum. So that is one takeaway you should remember. If someone says Carnot cycle gives you maximum work done, that's wrong. Carnot cycle gives you maximum efficiency. For maximum work done, efficiency need not to be maximum. There is one, maybe when you study Breton cycle in power plant engineering subject, there maybe you can look into this. But there is one derivation where you derive the efficiency curve versus work done. So maybe there you will find it. So yeah. Okay, so this is it. Now moving on. These plots you'll know, right? I mean, I'll just draw quickly only because I don't want to take more time here. But these were drawn by a professor also in the class. But you should also try to draw n equal to 0, n equal to plus minus infinity. And one process will be like this, and one will be like this. So, sorry, this is TS. So n equal to 1 here, n equal to gamma here, and these two will be like this only. So this will be P equal to C, this will be volume equal to constant. You should remember why this is there. Slope derivation was done by professor also. You can do it on your own also. If you do the TDS equation, from there you can get dt by ds for constant P and constant volume, and then you can compare also. So one question was asked to me also in one of the interview. You have drawn lines like this only. What happens in these regions? So I mean, there is no physical process which can occupy this region. That is the answer. Anyway, and PV plot, I think we draw this earlier also for PV plot in one of initial classes. If you do this way, it is plus minus infinity n equal to 0. And here it will be, it should be like this only. And one will be like this. So it will be n equal to 1, which is isothermal, and n equal to gamma, which is adiabatic process. So these things, I'll not spend more time. Then there is this equation, S2 minus S1 equal to mCp ln T2 by T1 for ideal gas. This equation, mR ln P2 by P1, and if you have volume, then it becomes plus mR ln V2 by V1. And if it is a solid or liquid, the second term is 0 because there is no pressure or volume change in compressible fluid if you have. So only MCP ln T2 by T1 remains. So now coming back to the one thing that I told you earlier in the last class, not long back, that what if you have finite source, what if you have finite source, finite capacity heat source and heat sink. So it was like you have a mass M1 C1. It's a solid basically. Don't solid or water you can take, and it is at temperature T1. One heat engine, reversible heat engine is operating, and it is taking heat from the finite heat source. And there is, for sake of simplicity, we'll consider same mass. Calculations become easier. Nothing more is there. Then there will be some work output. There is some, Q1, Q2 heat interactions, and the sink is at temperature T2. So this is a reversible cycle. So it's both internally, externally reversible. That is given in the question. And to find is what is one final temperature of this system, and second, maximum work done possible. So actually, since this is a reversible cycle, the work done itself is like the ideal case. By intuition, and obviously T1 is greater than T2, then only this whole thing makes any sense. Okay, so that is, you should, don't get confused there because if T1 is not greater than T2, nothing is holding here. So now what you do, we'll use the second principle, second law of thermodynamics, in a sense that increase of entropy principle is there, right? So delta S of universe will be greater than or equal to 0. So this is delta S of your system plus delta S of surrounding is greater than or equal to 0. Now we'll consider this whole thing, this whole source, sink and engine as our system. So, and we'll just, for sake of simplicity, we'll name this part as 1. There is the second component, and third component is your sink. So delta system will be S1, S2, S3, right? And there is, like, if the whole system is considered, consisting of all these 3 components, so there is no heat interaction in the surrounding. So this term goes to 0, and this is a reversible case. So this greater than or equal to becomes equal to. So basically, the equation reduces to this, and what is happening is actually this equality, maybe there is a slight difference here. In this case, delta S2 is associated with the reversible heat engine. It is 0 because the heat engine is reversible. But this equality is 0 because we want to find a maximum work output. In some cases, it can be greater or equal to 0, but there you will not get maximum work output. So, that to get the maximum work, you have to consider that it is 0. So, if you understand this point, then this further algebraic thing becomes easier. Now, let's say both final temperature of your system is Tf, which is unknown. So, what you can do is, 1 second. Okay, so you don't know the final temperature as well as you don't know. Uh, I mean, if you don't know that, you can't do much, right? So to find that, what you do, you use this equation 1. So basically, delta S of 1 will become MC ln final temperature TF, initial temperature T1. Correct? Then there is a sink S3, delta S3, MCP ln final temperature is TF and initial temperature was T2. Okay, so you can write it this way. So now what will happen? This MCMC you can take common and divide by 0. You'll get this thing. Now you know ln 0 is ln 1. Log of 1 is 0. So if you do that way, it becomes Tf square equal to T1 divided by T1 T2 equal to 1. So this gives you Tf is square root T1 T2. So this is your final temperature. And this is nothing but geometric mean of T1 and T2, right? Geometric mean is this. So now maximum work done, how will you find? Uh, Maximum work done is not that hard to find because uh, like, how should I say? Uh, Whatever with the internal energy change of source minus whatever is the internal energy change of sink, that will be your work done, right? So essentially, if you write the energy balance for this system, I will not skip that step, it is important. So you can write MC T1 minus TF equal to MC TF minus T2 plus W max. You can write max, right? So I think you should be able to get why I've written this. This is just the first law, like how whatever energy was lost from I should not use word internal energy, but that is same only here. It's a solid or incompressible fluid, right? So MC delta T lost by the hotter body will be equal to MC delta T gained by the cold body plus whatever work done we did. This is the energy balance basically. So now you have TF also, right? But before putting TF, you can just take uh, same terms on the uh, one side. So it will become TF plus T2 minus, I think, 2TF. Minus 2TF. This will be your maximum work done. Now, you can put TF value there, or you can do this way. You can just do a slight modification. Multiply and divide the whole thing by 2. So this will become T1 plus T2 by 2 minus, I mean, you understood, right? I took 2 from the bracket and outside. Why did I do this? Because it gives you a general expression. I mean, uh, in some subjective exams, this question was asked, and they said ki instead of 2 bodies, if you have n bodies, what will you do? So there you can modify this. You can write it n into MC arithmetic mean minus geometric mean. So n is your number of bodies. So here there are 2 bodies, right? So n is 2. Arithmetic mean is T1 plus T2 by 2. And geometric mean is this. We derived from the entropy, increase in entropy principle. So this is how you go. And you know, uh, one thing was there. In general, arithmetic mean is greater than GM. Actually, it is like AM is greater than or equal to GM, but I think equality holds when all the terms are equal to equal something. But in general, AM is one second. Is AM greater than GM always? One second. Actually, it's not equal anyway. I mean, sorry if any confusion is there. But AM is always greater than GM, so arithmetic mean is always greater than geometric mean. So W max will be always greater than equal to 0. So essentially, you will get some work output. How much will it be? That depends on your values, actual values of T1 and T2 and MC. So this is one case. Some people, they'll go ahead and modify this maximum work done formula also. I don't think it's required, but you can, just for competitive exams, if you want to remember, you can write this thing as MC into root T1 square plus root T2 square minus 2 root T1 into root T2. See, I have just written TF as root T1 and root T2, and T1 plus T2 term just in terms of their square roots. Why? Then it becomes A minus B whole square formula, right? So it becomes root T1 minus root T2 square. This is a nice expression. Maybe you can remember if possible. So that's it. That is for that case where you have a finite source and sink and maximum work done. And for that, what is the final temperature? Now there is one more problem in which you will have a adiabatic chamber and it is two compartment system. There are fluids in both the compartments, same mass, same capacity, but at different temperatures, and T1 is greater than T2. So one hot fluid and one cold fluid. You can consider hot water, cold water, or hot air, cold air, doesn't matter. But if it is air, the delta S formula becomes slightly complicated. So we'll consider hot water only, just to make our life simple or the expression simple. So now you consider this chamber as your system, and since it's a adiabatic chamber, there is no heat loss to the surrounding. So surrounding it is 0. So therefore delta S to the surrounding is also 0. So your delta S of universe is delta S of system, and your system has two fluids, two water compartments, 1 and 2. So it is basically delta S1 and delta S2, correct? So now and what we do, we rupture this membrane and let the fluids mix. So finally your system will be having twice of mass, heat capacity remains same, and at certain final temperature. Now you can find the final temperature quite easily because you can apply first law, and you can get whatever is the loss of heat from hot fluid, that will be T1 minus Tf. The same amount of heat will be gained by the cold fluid because there is no heat loss to surrounding, right? So energy balance essentially reduces to this equation, and you will basically get Tf as T1 plus T2 by 2, which is arithmetic mean. Okay. Now the thing is, in this question, I have not told you what is asked. I mean, because that is the whole point of doing this exercise. So basically, in this question, to find is delta S of system in terms of T1 and T2. or Tf and T2, it doesn't matter. So you can write it as, again, the principle of increase in entropy as delta S of system as delta S1 plus delta S2, correct? Because surrounding is 0. So, I mean, anyway, this is your, what should I call it, delta S of your universe, since surrounding is also 0. So this has to be calculated. So what will we do is, since this is an incompressible fluid, hot water, we have this formula, right? MC ln final temperature by initial temperature plus MC ln final temperature by initial temperature. So now you can just put these terms together. So it becomes Tf square T1 by T2, right? But this doesn't give you any insight. The whole point of doing this exercise was to, slightly modify this thing. One second. Tf by root T1 T2, correct? Now if you see, the Tf is nothing but the arithmetic mean. So you can just write it as arithmetic mean by geometric mean of your source, your initial and initial temperatures of hot and cold fluid. And we know AM is greater than GM always. Therefore, delta S of your system will be greater than 0. It cannot be equal to 0. Therefore, this is a exercise which proves mixing of two fluids is an irreversible process. So I think some of you may remember we studied internal irreversibilities, external irreversibilities. External is because of heat transfer from system to surrounding, and internal is because of 4 factors: friction related, this mixing of fluids, uh, unconstrained expansion, like expansion against vacuum. So this is an exercise which proves that mixing of two fluids is a irreversible process. I understand the problems that we are supposed to solve in this discussion are more or less numerical. But anyway, I thought when I was preparing for different exams in my time, I studied these things. So maybe some of you will be helped if we study this thing. So I think that is it. Actually, there was one more problem, but we don't have time. We can take some numerical problems so that your assignments will be easier to solve. But if some of you are interested, I can give you a problem. It will be like theoretical, like this, not theoretical, I mean analytical derivation only. One second. Where was it? It was based on this only, like for a reversible adiabatic process, you get PV power gamma equal to C, right? But in some cases, like that thing itself is slightly modified, and you get sort of a similar expression, but in other form. Let me see if I can find that question. It was like for I think ESC previous year question. It was subjective exam. Yeah. So the question was, I'll write it for you. Maybe we'll not solve this time. Maybe next time, or if any one of you can solve, that will be better. You can find this solution everywhere. I mean, I don't think it will be that difficult because it's a previous year ESE question. But anyway, this is a good exercise since you have done this part of course by now, right? So anyway, the question is there is a gas. It is not mentioned which type of gas. Okay, so don't assume ideal gas everywhere. A gas which follows PV minus B equal to RT. This is the governing equation for the gas. B is constant, it's not a variable. Also, internal energy of the gas which is U is given as CVT plus some another constant K. Okay, so now if this gas undergoes isentropic process, then prove that PV minus B power gamma equal to constant. So this is a theoretical, not theoretical, but analytical type of question. So I hope some of you can solve this. You can take your time. If you want, I can also solve, but I think it's good if you solve this on your own. Maybe you'll get some sort of satisfaction. Nothing else is there. So yeah, the way it is solved is basically you have this governing equation, right? P into V minus B equal to RT. So you get the T value, like T will be P V minus B by R. So what you do, you put this T value in one of the TDS equation. So basically you have this TDS equation, right? TDS equal to du plus PdV. Now you may ask why we are deriving du plus PdV. The reason is because we have given in the question some internal energy equation is given. So you can use TDS equal to du plus PdV. From there you can get, and since this is a isentropic process, ds will be 0, right? So you'll get some expression in which your internal energy will be related to the pressure PdV term, right? There will be du plus PdV, which will be equal to 0. And then you can do further simplification and use this governing equation also, P equal P V minus B equal to RT. And finally, you should get the desired equation, this desired expression. Try to solve this if you can, that's good. If you are unable to, maybe next time we can solve this. So I leave it up to you. If you want, we can solve. If you don't, that is also fine. So anyway, yeah, you can take this as an exercise. Maybe 3 people are here. You can see, and if not, let me remind me next time we can solve this. So now coming back to your assignment type of questions, which are also important. So I saw some previous year assignment. So there were a couple of theoretical questions. So now the first question was related to the entropy of isolated system. So first of all, you should know what is isolated system. Isolated system no energy and mass interaction. Okay, interaction, transfer, both are same. No energy and mass interaction with the surroundings. So this is your isolated system, right? So now there are four options, like entropy of isolated system remains constant. It always increases, always decreases. It may increase, it may decrease. So like this is also a very common question in competitive exams. So essentially, you just write your principle of entropy increase, which is delta of system plus delta S of surrounding. So in this case, delta S of surrounding will be 0, right? Because there is no interaction with the surrounding. So essentially, your system and surrounding are same. So now, how will you write your delta S of system?
सर रिवर्स ना होता वहाँ पे।
हाँ
सर डेल्टा एस जो होता है सिस्टम विल बी डेल्टा एस सिस्टम प्लस डेल्टा एस सराउंडिंग इक्वल टू डेल्टा एस।
हाँ सॉरी ये यूनिवर्स होगा, ठीक है।
यस सर।
हाँ तो ठीक है, तो ऐसे करोगे तो डेल्टा एस ऑफ सिस्टम इसे जनरली हम लोग कैसे लिखते हैं, इंटीग्रेशन ऑफ डेल क्यू बाय डेल टी प्लस सम डेल्टा एस ऑफ entropy generation, source of entropy generation. Yeah, in this case there is no heat interaction with the surrounding, so this goes to 0, and we know this term is always greater than 0, always positive. So basically it is non-negative. Non-negative, yes, non-negative. So basically, I mean, you can write it positive also. Okay, we'll write positive only. So this is always positive. So when it is isolated system, its entropy always increases. If everything in that system is reversible, then it may remain constant. But if it is a general isolated system, nothing is mentioned, you can say it will always increase. Only if all the processes inside that isolated system are reversible, then it will remain constant. So that is one question, one type of insight. Then yeah, I mean, this part the professor also took in the class. Delta S of universe has to be greater than or equal to 0, but that essentially means this summation system plus surrounding has to be greater than or equal to 0, but this can be positive, negative, or 0, and this also can be positive, negative, or 0. It's just that their sum has to be greater than or equal to 0. So many a times they'll say delta S of system has to be greater than 0. So just keep in mind the language of the question. Now, maybe some numerical we can do. One second. So yeah, actually this is ammonia. So I don't know the properties are available with you or not. But anyway, I'll tell you whatever properties are required for this problem. So there is a container, rigid container, like this. It is an insulated one, no heat interaction with the surroundings. There is one chamber, membrane. There is like two compartments, both have ammonia, same gas. Total volume 200 liters, and this partition is equal, so each one is 100. On this side, the pressure is 2 megapascal, temperature is 200 degrees Celsius, and here in the B compartment, pressure is 200 kilopascal, which is 0.2 megapascal, and the temperature is 100 degrees Celsius. Then we break that membrane by doing something, and final temperature is equal to 70 degrees Celsius. Your system comes in equilibrium and final temperature is 70 degrees Celsius. Your surrounding temperature is 20 degrees. I think it's not adiabatic. 1 second. Yeah, in question it is nowhere mentioned that it is adiabatic. So my apologies. I gave you wrong data initially, because if it is adiabatic, then there is no no use of surrounding temperature, but it is given that surrounding is at 20, so that it has to be non-adiabatic. And you need to find what you need to find. First is what is the work done between initial and final state. And second part, you need to find, I think, the total entropy change of universe because of this thing. Yeah, this is the thing. Actually, for such type of problem, wherever you get this rigid container type of problem, my personal advice is to take this whole thing, whole rigid container, as your system, because then you don't need to worry about what is happening inside. Your boundary is covering the rigid container, right? And normally there is no movement, so your boundary work is 0. So therefore, the first question itself becomes 0. But like if someone takes only compartment A as a system, what will happen? Whatever work is done by that A on B will be equal to whatever work is done by B on A, or there will be some you'll have to apply both first law and second law. I mean, maybe I'm wrong, but I mean, maybe these work done will be not same, but it will satisfy first law and second law, but applying to each compartment is difficult. You can try if you want, but essentially it will become 0, because for a whole system it is becoming 0, right? So whatever complicated thing you will do, it will become 0 only in the end. So yeah, this is again like a mixing of two gases case only, but here you have numerical values. So anyway, the first part is 0. Second part is interesting. For second part, you can write it as delta S of system plus delta S of surroundings. Delta S of system is delta S of A plus delta S of B, correct? So if you do that, then what you can do is this delta S of surrounding will be some Q in process 1 to 2. This we know that W1 to 2 is 0 by T0. I am not giving a sign here, that will come out of the first law. So what you need to do, you can apply first law. So then you can write Q1 to 2 is W1 to 2 plus delta U. Like, I mean, instead of delta U, you can write U2 minus U1. This is 0. U2 will be M2 into small u2 minus m1 into small u1. So now you don't know m also, right? In question, like in the given data, Cp for nitrogen is given as 1.042 kilojoule per kg Kelvin. Cv for nitrogen is given as 0.745. So if you don't have a property table for nitrogen in the question, you can assume it as an ideal gas and use U equal to CVT to find the this thing, this change Q1 to 2. So it will essentially become M2 T2 minus M1 T1. Now you don't know M1 and M2, right? T1, T2 you knew. Actually, it will be for first gas, then there will be second term for second gas, right? Because both gases, their entropy is changing, right? So this will become MA CV T2 minus TA1. Essentially your final temperature. This is your T2 is nothing but your final temperature TF plus mass, whatever mass was there in container B, CV into TF minus TB1. What is the initial temperature of B container? So now the question is how to find, because temperatures were given, right? So these are known, CV is given, MA and MB are unknown, right? So how to find them? That is the question, right? So you can, again, if you don't have any additional information in the question, you can assume it as an ideal gas. So basically, what will be the MA? MA will be PA1 VA. Actually, this is initially whatever was the pressure inside the A container, A part of the container, volume of the A container, R for nitrogen and T1. Correct? TA1. Just to, I don't want to abuse the notations, so I will write 1 everywhere. So these values were known. This was 100 liters. This was, I think, 2 megapascal. R for nitrogen, you should be calculating this. It's not a universal gas constant. If you do that, 0.297 it will come in standard units. And TA1 was given as what was it, 200 degrees Celsius. Keep it in Kelvin because this is an ideal gas equation. So it will be 473 Kelvin. So if you do that calculation, basically MA will be 1.424 kg, and similarly MB will be 0.1806 kg. See, mass in the B was very low because pressure is almost 10 times lower and temperature is also 2 times lower. So that's why mass in the B is very low. It's almost 8 to 9 times lower than the A. And since finally it is mixing, so there also you'll need the total mass. So better to calculate here itself. It will be 1.6046. So now final mass, final temperature also, and total volume. So even if it is not asked, you can calculate MRT2 by V, right? This was 200 liter total volume, total mass you just calculated. This T2 is nothing but TF, your final temperature, which was 70 degrees Celsius. So put it in Kelvin. That is a very common mistake. If you do that, you'll get 817 kilopascal. So this value is somewhere in between 0.2 megapascal and 2 megapascal, right? So this is a sanity check you can do when you get any answer. When two fluids at P1 and P2 will mix, their final temperature will somewhere in between the two extreme values, right? So it is 0.8 megapascal, so which is okay, that makes sense. Now the second part, which is delta S of your, oh sorry, before going there, you can calculate Q also right here, which was, now you know MA, MB, you know all the temperatures, CV value is also known. So you need to put it in that formula, and you'll get the Q2 as 141.95 kilojoule. So basically, heat is lost from system to surrounding, right? Because of our usual sign convention, when it is negative, we are losing the heat. And then now come back to the delta S calculation. Delta S of your universe, or some people call it net delta S also, but it's okay to use universe also, no issues. Delta S of A plus B, A plus delta S of B plus delta S of surroundings. So now for A, again you are assuming ideal gas, right? That's why you are using ideal gas equation there. So here also you can write that formula, right? MA Cp ln Tf by Ta1 minus R ln P2, which is final pressure, by Pa1. And similarly for SB, you can write MB into Cp ln Tf by Tb1 plus minus R ln P2 by Tb1. Now the question is, see, the heat is lost from the system to surrounding, but surrounding ko to heat mila na, the surrounding received the heat, right? So here you should write Q as positive, because and the temperature is 20 degrees Celsius surrounding, so that is 293 Kelvin. This is your delta S by delta S for surrounding. Don't get confused. See, this negative sign is because it is lost from the system, but for surrounding it is addition of heat, right? And when heat is added to the surrounding, its entropy should increase. Therefore, there should be a positive quantity. So if you do this calculation, it's a big calculation. Actually, I was wondering, instead of P2 by P1, can we do V2 by V1? MR, 1 second, R into ln P2 by P1. V2 is 200, right? Anybody? Narendra? Or Priyanka is still here? We'll stop after this, okay? I know it's late.
Hello, sir.
No, I asked one question here. See, we can write this Cp ln Tf by T1 minus R ln P2 by P1, right? But we
Yes,
can
sir.
also write it as Cp ln Tf or T2 by T1 plus R ln V2 by V1, right?
Yeah.
So, like, should we write it that way? Will the answer change? Because see, your initial volume was 100 liter for both. Final volume is 200 liter. Initial pressure was some 2 megapascal, 0.2 megapascal. Finally, it became 0.8. You can do this exercise. We are getting late here. Maybe next class you can tell me whether the answer remains same or it changes. Ideally, it should remain same, right? It should not
Okay,
change.
sir. Okay.
So please, if you can, just look into this. I'll give you the final value. This this delta S plus, like delta SA plus delta SB, this term comes out to be minus 0.1894, and this delta S of surrounding, which is this term, it comes out to be 0.4841. So basically your delta S of universe is 0.2947 kilojoule per Kelvin. It's a capital K. Okay, so it is greater than 0. So this is a possible process. You may find some examples in which the question is asked, some process will be given, and they will ask whether this process is possible or not. Please determine. Or you'll come across some question in which they'll say ki there is one inventor who claims to be he who claims that he has designed a new machine for certain temperature and pressure, and it is giving efficiency higher than the Carnot cycle. So the question will be, please verify his or her claim. So there you have to do this calculation. You have to calculate delta S of surrounding, then delta S of system, delta S of system, then surrounding based on the heat interaction. And then if the total delta S, which is delta S of universe, if it is coming, it should be greater than 0. So if that is happening, then you can say that claim of the inventor is correct, and this system is feasible system or feasible process. There are other questions actually I wanted to take, but I think the time is getting over. So anyway, we'll leave it at that. Maybe if you have any questions, you can ask me next time. So we'll stop here. Do you have anything about the assignment solutions or anything else? Narendra, Priyanka, you can tell me.
Yes, sir. In the last assignment also, in one of the question of that is my power plant, enthalpy thermal efficiency calculation is wrong. In the solution, actually heat supplied is given 1 megajoule and solution provided for 1.5 megajoule.
Assignment number 7, huh?
Yes, sir.
1 second.
Question number, I think.
Power plant 4, I think.
4.
In a steam power plant, 1 megawatt is added in the boiler, 0.6 megawatt is taken out in condenser. Pump work is 0.005. Find the plant's thermal efficiency.
Sir, for 1 megawatt efficiency is coming 40%. That option is not available, so none of this is the correct answer. But in a calculation in the solution, it is taken 1.5 and calculated 27%.
1 second, I'm opening the solution PDF. It is loading. 1 second. Question number 4. Huh? I don't know who prepares this. Anyway.
Because 1.5 is not given anyway in the question.
Yeah, but did you understood the question? Did you understand?
Yes, sir.
Generally, I think the point is, I mean, maybe there is some simple mistake here. It should be 0.4 by 1, right? So 40%. Huh?
Yes, sir.
But it is 1.5. Okay. Total heat supplied. You supplied heat only in the boiler, right? You don't supply it anywhere else.
Yes, sir.
They have used 1 in the work done by turbine calculation, but they are not using for
The
efficiency.
ranking cycle is any given. Steam power plant cycle is given.
Okay, so this is I think it's a clear mistake. Anyway, so anything else? Like only this or?
Hello.
Yeah, Priyanka, go ahead.
Sir, I have doubt in question number 6.
6 of last assignment?
Yeah, last assignment, sir. Refrigerator. Work
Okay.
input of work input which is needed to make ice cubes. I didn't understand the solution part, the beginning one, that they in the solution part they have taken water tray as control volume.
Okay.
So could you please explain that till the calculation of the heat transfer?
Okay, 1 second. I'm just reading the question. Refrigerator is making ice cubes out of a tray, 0.25 kg water at 10 degrees Celsius. Assume that refrigerator has beta 3.5. Beta is what? COP.
COP.
And a motor compressor of 750 watts. Okay. We assume constant pressure process. Work done is PdV. Okay. Q1 MH1 minus H2. Consider refrigerator. COP is QL by W in. Okay. So W is 26.81. H1 and H2 values are taken from the water tables. Okay. Like, what is your doubt here, Priyanka? I mean, which part
Regarding the calculation of heat transfer,
Q1 to 2?
like Q1 to 2, yes. So
Okay.
how is it? I mean, how water tray is to be considered as control volume?
If you are not satisfied, consider it as control mass. Like, see, you have this mass of system, right? I mean, I would not have this.
Hello, sir.
Narendra,
In this problem, water tray is not the control volume. Water is the control volume. Water should be the control volume.
Correct. Yeah, because they have said that water has control volume and then they are neglecting its mass.
Yeah.
So just assume water as a control volume or control mass, right?
And
So,
we have to neglect the tray.
Anyway, I mean, they have done this way, but one way I was thinking is, see, you have water at 10 degrees Celsius, right? So, to make it as an ice cube at, let's say, 0 degrees Celsius, how much heat you need to take out? That will be MCP delta T plus MHFG, right?
Yes.
So, you have 0.25 kg water. You can take CP as 4.18. Initially, you are just cooling it from 10 degrees Celsius to 0 degrees Celsius. So, that is MCP delta T. But at 0 degrees Celsius, to convert it from liquid to ice, you need to take out the latent heat of fusion. They call it, right? Latent heat of freezing, I think. Anyway, matlab liquid to water it is, water to ice it is going. So M into HFG, if you do, that will give you Q1 to 2, right?
Okay.
Essentially, they are doing same thing only, but this is a confusing way of writing. And they have not mentioned that they are neglecting that MCP delta T. It will be very low value. We can solve this here itself. Do you have steam table with you, Priyanka?
Steam table, yes, sir.
So I just need HFG value from you. If you can see my screen, I will just write it as MCP delta T plus MHFG at 0 degrees Celsius. So M is common, 0.25. CP of water is 4.18 kilojoule. It is 10 degrees Celsius difference. So 10 minus 0 plus the HFG of water at 0 degrees Celsius, which will be Hg minus Hf. So can you tell me that value?
2501.6
Kilojoule per kg, right?
kilojoule per kg.
Yeah, so see this term, this MCP delta T, it is 41.8. This is 2501. So basically what they are doing is they are neglecting this term, but you should not do that. So if you do simple calculation, 41.8 plus 2501.6 divided by 4, so you'll get Q as 635.85 kilojoule. And what they are getting here is they have not mentioned.
There it is mentioned as 93.8.
93.
Sir, hello, sir.
Yeah.
I have any calculated and I got the answer same. That HF value, that temperature is given at 10 degrees. You'll get the HF value at a 10 degrees centigrade plus the latent heat of the fusion, that is 333.6. You'll get a 93.8975 minus.
Oh, acha, this value, huh?
Yes, sir.
This 2501.6, it is for which then? Which is, what is this?
I told it for water at 0 degrees Celsius. Isn't it for water?
It should not be then. I think it is for
It is
water
the sir,
to
latent heat of
water.
fusion, sir. It is the
I
latent heat of the fusion, and its standard value is the 333.6.
Acha. I think this 2501, it is for water to vapor. I think, because I remember when you boil 1 kg of water, you have to give some 2500 kilojoule of heat.
Because here
Priyanka,
we
you
are
can.
converting the solid to water, ice to water. So it
Yeah, yeah.
should be the latent heat of the fusion.
Yeah, steam table is not right because steam table is for liquid to vapor.
Yeah,
But
yes,
here
sir.
we are using this thing, what do you call ice to liquid, right? So it is fusion. And this 2501 value, which Priyanka told me, that is vaporization, latent heat of
Yes, sir.
vaporization. So, okay. So if you take 333, then I think now it will match. 41.8 plus 333 divided by 4. So, yeah, so 93.7 kilojoule. And they are getting 93.85. So it's okay. So, yeah, then I think the other things will match only because it's just division by 3.5. So anyway, Priyanka, I think the point is here that 2501 we should not use for this question. That
Okay.
2501, essentially it says when you want to convert water from like liquid water at 0 degrees Celsius to vapor at 0 degrees Celsius, but I don't know that that state of system is feasible or not. So anyway, the moral of the story is if there is ice involved, don't use steam table. I think that is a takeaway. And this is a this is a tedious way of writing this Q12. It is ought to be confusing, but anyway, you can do this way: mCp delta T plus mHfg at 0 degrees Celsius for ice and water, liquid water. So maybe this will clear the confusion. So is it okay?
Yes, sir. It is. I understood now. Thank you, sir.
Oh, okay, no issues. So shall we stop? Narendra, Priyanka?
Just 1 minute, sir. Our Mars are not modifying until now, sir.
I told them I told them
Yes, sir. We are doing this in a course very interestingly and solving the assignment. But even our solutions are correct. We are not getting the marks. But other students, they are just without any solving, so they are getting the marks.
Yeah,
It
yeah,
is
I
a
understand your point.
industry. It is an industry, sir. याने. Sir, even in the next assignment, in 2 questions, there is a mistakes.
You are able to see my screen, right?
Yes, sir.
So see, I have written this mail on 30th September.
Yes.
In assignment 5 and 6, you told me, na, there are some questions that are
Yeah.
good, correct and all. So professor also replied that thanks for bringing to our notice.
Yeah.
But after that, what happens? It's not in my hand, right? So
Okay, sir.
I understand your frustration, and it should not happen, but it is happening. So I mean,
No, sir, it
what?
is not like a frustration. But anyway, it should not happen.
Yeah, your argument is well taken, but unfortunately, I have done what all I can do.
Sir, even in the next assignment and assignment date, in a question number 3, it is for the 2 kg of the water, and answers are calculated for the 1 kg.
What we'll do, Narendra?
And even in question number 4, that calculation of the entropy of the surrounding is not counted. That answer is given for the system only. No doubt, I calculated that answer and correct it.
Mm-hmm.
Yes,
Anyway,
in the
the
question, the
solution is
entropy of the
the solution
surrounding
is
is not considered.
the solution is not yet uploaded, right?
Yes, sir.
We'll wait for it, and if there is one problem in assignment 7, then there is 8. So maybe we'll make a list of 2, 3 such things, and then again
Yeah.
forward it. We'll
Mm.
see if anything changes. And don't you have any other forum that, like, any other way to contact anyone other than forum?
I mailed to support NPTEL supports.
Any reply from them?
No.
Achha. Anyway, we'll see. Maybe now it is getting late. Next time we'll see.
Yeah, yes.
Okay. So
Okay. Thank you, sir. Thank you very much.
thank you. Welcome.
Thank you, sir.
Yeah. Thank you. So shall we stop now? It's already
Okay, sir.
half late.
Okay, sir.
Sorry for
We are too late.
Yeah. Okay, then we'll stop now.
Okay.
Okay. See you next Tuesday. Bye.
Okay, sir.